Herstein's Abstract Algebra 3rd edition, Chapter 2, Section 1, Problem 5. In example 9, we want to show a few things. So one, we're going to show that this G star F equals F star G inverse. Then we'll show G as a group, non-abelian, and of order 8. So what is our example 9 here? This is an important example. You really want to have a good hold on this. This will really help you understand the dihedral group later on in abstract algebra. And it also really shows there's some key themes in this problem that come up a lot. So example 9 here, we have that S is the plane, and that's just a set of all x, y, such that x and y are real. So that's literally the Cartesian plane that you think of with the x and y axis. And then we're going to consider two mappings, f comma g. I know they're mappings or functions because they're part of A of S. Remember, A of S is the set of all mappings from S to itself. So F and G map the Cartesian plane to itself. How do they do that? For every point in the plane, f of x is going to send it to negative x, y. And then G will send x comma y to negative y comma x. And what that really is, and it's important to keep in mind what's going on here, f is just a reflection across the y-axis. So that's just flipping from left to right, right to left. And G is a rotation 90 degrees in the counterclockwise direction. So now we're gonna use these two mappings to define a group. And every element of our group is going to be a composition of mappings. It's going to be f to the power I composed with g to the power j, right? And keep in mind, the reason why we're saying I equals 0, 1 here, well, if you flipped over the y-axis twice, you would go from right to left to right, or vice versa. So you would just end up where you started. So really, f squared is the identity. So there's no reason to have I be greater than 1. Well, what about g to the 4th? What happens if we rotate 90 degrees 4 times? 90 times 4 is 360. We just rotated in a circle, and we got back to our original position, x comma y. And then that's the set of the group, so we need an operation. Whenever we're dealing with AS, which is the set of all mappings from S to itself, the operation is always going to be composition of mappings, which we'll see in a second here. So here's some reminders of what we need to know, which we'll refer to. First thing the problem asks us to do, G star F equals F star G. The actual computation isn't complicated here. What I do want to highlight, though, is what is this saying? So one, what is composition, or what is the product? So star here we're using for the product of the group. But G star F, this is our left-hand side computation. G star F is literally just composition of functions here. So it's just G of F of the ordered pair, x comma y, right? Now, what does this actually represent? Well, remember that the F here, which is being applied first, is flipping over the y-axis. And then second, we're going to rotate by 90 degrees. So what this is saying, if we show this is true, is that if we flip first and then rotate, that's the same as rotating in the opposite direction and then flipping. Okay, and that's one of those ideas that comes up a bit, especially with the dihedral group here. So this is our left-hand side. We show that it equals negative y comma x, negative x. And then this is our right-hand side here, where we did have to solve for g negative 1. You just need to follow our definition of g of x, y backwards. And to make sure you did it correctly, we could just apply g to the ordered pair y comma negative x, which would then give us x comma y. So we know that's our inverse of g, and at the end of the day, we get the right-hand side equals the left-hand side. So that's the first thing that we're asked to do. The second thing is make sure that G is a group. So the procedure for proving something's a group is always the same. It needs to have it needs to hold all 4 of these properties. So we'll start with G is closed. And we're going to take a pretty inefficient way to show this in order to help build your intuition. Because again, this is an important problem moving forward. So the product of two elements. To be closed, you apply the group operation to two elements, which would look like this in this case, and you need to make sure that it's still a member of the group. Now remember, to be a part of this group, this is what you need to look like. Your exponents have to be within that range, and the f, it's fg, not gf, which we'll see in a second here. So the product of any two of these elements Well, it's just going to equal, it's literally just going to be f to some power, g to some power, f to some power, g to some power, where we're limiting these exponents' powers here. The question is, can we rearrange this somehow in order to make it look like an element of g? Well, let's look at what happens when k equals 0. So if the second f has an exponent of 0, so instead of flipping, it just is the identity element, then what does this look like? Well, what ends up happening is our g's just get next to each other, right? So that's what this looks like here. And then we have that our element is now f to some power, g to some power, which is essentially what this is right here. But the key point is that the g to the j plus l, well, that might not be 0, 1, 2, or 3. So what we need to do is if it's more than 3, we need to reduce it down to a form that looks here. And this is one of the key points for this problem is what we can do is multiply by e on, pull out g to the power 4. So this is just g to some exponent, right? So if it's bigger than 4, we can just pull out a g to the 4, and then we know that g to the 4th, which is rotating by 90 degrees 4 times, is just e, and then this guy will have the correct exponent, right? That's the idea here. So this is the simple case where we just get our two g's to link up, and then we can just reduce that exponent by basically saying if you want to rotate 6 times, that's the same as rotating 4 times plus 2 times, and we know that rotating 4 times is going in a circle, so let's just ignore it. That's the idea that's going on here. Now, if k equals 1, this isn't going to work, right? We can't just combine exponents. We don't have that fg equals gf. We can't swap these elements around. So we need a way to move the f, our second f, to the left of that g. And that's what we're going to look at right now. So I'm claiming that this is true, that fg to the power 3 equals g to the f. And remember that this is what this follows from what we already proved. So up here, we already proved that gf equals fg inverse. This idea of taking two independent actions and figuring out how to swap them in the order of the composition is very important. So in this example, it's basically what we just did. We know gf equals fg to the negative 1. So we can either stick with the negative 1, or I just multiplied by e, and we know that e is just rotating in a circle. So 4 plus negative 1 is 3. So gf equals fg to the power 3. And how does this help us? Well, I'm just going to show this by example to be very deliberate about this. So what we can do is take this g to the third, right? So I'm just doing an example where this g is to the third and the f is to the power 1. And we can make that g squared g1, and then it's followed by an f1, and that's what I've highlighted in red here. So for every time we have a g where it's not supposed to be, we can take one of the g's out. So that's what this g1 f1 is. And then I highlight in red, well, that's gf. g1 f1 is just g star f, which we know, what does g star f equal? G star f equals fg to the power 3. So what we basically did is we traded one of our g's to the right, and that's what is the first step there. So now we have a g squared times an f1, and I'm saying, well, that's just g1 f1, which is then g1. Then we can swap the f and g again, right? So I've highlighted in red every time we're doing this, right? So because this was a g to the power 3, we did it 3 times, and every example comes down to that. And then once you swap everything, you get f to some power on the left and g to some possibly very large power on the right. But we know from our last slide, if we go back, that we can always just reduce, right? We can pull out g to the power 4s, and on the left we could have pulled out f squareds if needed. And so no matter what these exponents down here are, we can always pull out f squared, which is flipping left, flipping right, or g to the 4th, which is rotating in a circle, to reduce our exponents as needed. So that shows that we are indeed closed. For associative, which is our second group axiom, it looks like a whole mess, right? But remember, associative, we just need to check this equation. And in our case, composition of functions is associative. So even though we have 2 functions per element and there's 3 elements here, so we have 6 different, indices flying around, I could have also just written, done. This is associative because composition of functions is associative. So this is the formal way to write it, but really composition of functions is always associative, so you don't need to worry about it. Number 3, the identity element, it's exactly what you think it is, and you can check that. For the inverse condition, just think about what the exponents need to do. G to the negative j, f to the negative I should do the trick, and in fact it does. And then we check the other side. The only thing we got to be careful about is that this element actually belongs to G. Remember, G has to have these correct exponents. But hopefully by now you see how to do this, right? So we need to move f over to the left, which we've shown we can do, and then we need to make sure that the exponents are in the correct range. So here I did the work to make the exponents be in the correct range, but don't forget you need to also make the f go on the left-hand side there. So that shows that G is a group because we checked all 4 axioms, right? Now, this is non-Abelian, and that should make sense as far as flipping and rotating, right? You should come up with a couple examples in your head about why flipping and then rotating is different than rotating than flipping. Actually write it out, because this is going to come up a lot. This is a prime example of a non-Abelian group. When you actually write it out, FG doesn't equal GF, so you can just say it's non-Abelian, but keep in mind that this is an important example. And then, how do we know this is of order 8? Well, I can tell you by looking here, it is at most of order 8, right? There's only 8 options. I have 2 options for I have 4 options for J. 2 times 4 is 8. But we do need to make sure that all of these combinations are unique, right? And this is what we do here. None of these on the right-hand side equal each other, and so we know that they are indeed unique. This, like I said, this is about the dihedral group. Is a very important example. So please don't skip over this one. Make sure to like and subscribe while you're here. Appreciate the support. If you have any questions, make sure to ask them in the chat.